Hi everyone. Today I am going to explain d-Orbital splitting pattern in tetrahedral complexes. In last class I have explained you d-Orbital splitting pattern in octahedral complexes. Here we have a complex variation, that is tetrahedral, right? So to explain the d-Orbital splitting in different complexes, certainly we have to know the two things, right? One is the d-Orbital shape, right? The lobes arrangement with respect to of all three coordination axes in 5 d orbitals will be perfectly known to us. That was already discussed in previous classes, right? Previous videos. The second thing is the structural aspects, or we can say that the ligand orientation in complex bonding with metal, right? The ligand bonding with metal in a complex we have to know with respect to of coordination axis. That will gives you what orientation of ligands is approaching towards the metal, and when it is approaching towards metal, how it is affecting, which type of orbitals going to be affected with the ligand approach. Thus will gives you the exact splitting pattern of exact d orbital splitting pattern in different complexes, right? So here we are going with the tetrahedral complexes. The known uh, pictorial diagram of tetrahedral is this, right? The anyone, if you want, if say to draw the tetrahedral, most of the body will express the tetrahedral in this manner, right? Here projection of tetrahedral here in this manner, it may looks that all the four ligands in an one plane, and it is an two-dimensional structural tetrahedral complex. But the tetrahedral complex never be two-dimensional complex. It has the three-dimensional structural aspects. So this representation, what it shows the four ligands in an one plane, it is not correct. The four ligands what it showing, they are not in one plane, they will be in different planes, right? So that when we take in an like this structure, this is what the tetrahedral, isn't it? If this is the middle one is metal, the upward one ligand will be there, and front side, right, front side downward three ligands. In three of down, one is exactly front, right, sharply front in angular. The other two are back side, angularly they will positions, right? The front side one ligand, upward one ligand, in downward three ligands. In downward three ligands, one sharply towards the front, the other two are angularly in the back side, these two, right? That is what the tetrahedral, right? This is known to you, right? Same the structure here it is represented, this one is same, right? Here all the ligands never be placed in an one plane, right? These three ligands and this fourth ligand is differently positioned, right? So this, once if we look into a different orientation, you will get this particular second structure, second orientation of tetrahedral, right? So to get this, what I do, that I just tilt the shape of here, I just tilt the shape slightly, I will do this. What happened here, I didn't change any chemical change or any structural change. I just done that I just pulled the upward ligand into a slightly angular, right? And I am getting that these two left and right ligands into one plane, right? Now the left and right, what I am having, the right and left, right, in an one plane, on one plane I am getting, right? So this is what, it clear? This ligand and this particular ligand both are on one plane, right? On this surface we are keeping, right? Where what happened, the other two ligands, the one is becoming upward, the other is becoming downward of with respect of this plane, with respect of this particular plane. One is becoming upward, the other is becoming downward, right? The left two are in one plane, the left two are in one plane, right? So what happening, these two planar two ligands are in an V shape and they are in on plane. The left two above and below are in another V shape where one is upward, the other is downward, right? Such same representation I given here, isn't it? The two ligands in an one plane, in angularly one plane. The other left two with respect of this angular plane of LML, LML. The third ligand is above, maybe above. The fourth ligand will be in down. The fourth ligand is in down, right? Like that we got, right? From this only we will get this, right? Here what happening? One V is in planar, if it is in planar, the other V is in a non-plane, right? The other angular bonding is in a non-planar, right? Which saying that this V shape and this V shape are opposite to one to other, right? Isn't it? This V shape and this V shape is opposite to one to other or not, right? This left to right V shape is in one plane. The above and below is in another plane. This particular V is exactly perpendicular for this particular V, isn't it? Right, 90 degrees it will have, right? So that is what here I show in. Same that when we incorporate this particular structure at the cube, in the cube, right, we will get this, the ligands will be occupies the alternate corners and metal in the middle. So when there it is happens, this is what the upward V, right? This is what the downward V, right? This particular V and this particular V is opposite to one to other or not, right? Right. If same structure, if we are molding like this, what happening? Upward one V shape, downward another V shape, right? Downward another V shape. Upward V shape and downward V shape is a two opposite in direction, right? Downward left and right, upward is front and back, right? Upward is front and back, right? That is what we are getting, right? So same here it is getting in upward front and back, in downward left and right, downward we are getting left and right. That's how the structure in cube, tetrahedral structure in cube, it will be has, right? Here after getting the tetrahedral in cube, right, we have to be keep the all three coordination axes. We have to add all three coordination axes, right? Once we do that, the left to right will be x-axis and top to down will be z-axis, front and back will be y-axis, right? Front and back y-axis, left to right x-axis, top to down z-axis, right? That is what we will get. So writing the statements, in a cube the tetrahedral complex has centrally situated metal ion and the four alternate corners will occupy the ligands, isn't it? What happens once we keeping the tetrahedral in cube? What happening? The central position is occupied by the metal ion, and the all alternative four corners of the cube were occupied by the ligands, right? That is what. On addition of coordination axis, x, y, z, right? No ligand passing along the coordination axis, right? Isn't it? When we keep this all three coordination axis and looking the ligand position with respect of all three coordination axis, no ligand is along the coordination axis. On x-axis there is no ligand, on z-axis there is no ligand, on y-axis there is no ligand, right? Is it clear or not? Right. So as I just now said that the on any of the coordination axis no ligand is present, right? So on addition of coordination axis, no ligand passing along the coordination axis. This is by this picture we can come to know, but I will explain you in a model also. Here I taking the model where we are getting, this is what the z axis, right? And this one is a x axis, and this we are considering y axis, right? In previous statement what we said that when we kept this tetrahedral in an cube, the ligand occupies the alternate corners, right? So when the coordination, when the ligand has to pass uh, through the coordination axis, means the coordination axis either they has to pass through ligand sites, or along the coordination axis we have to get ligands, right? So we are getting the ligands in n corners, right? In alternate corners we are getting the ligands, right? But the coordination axis where we are getting at the middle, at the middle of cube we are getting the coordination axis, either it may be z or x, or it is y. They are all passing at the center of the faces, right? This is the face, right? Top face and down face. In the top and down, middle it is passing the z axis, where the ligand sites are on the corners, on the corners of the cube, like that. No axis is passing through any of the corner sites. So it means that the no ligand will passes through coordination axis, right? That can be clearly here it is shown, right? This is what the z axis, right? Top and down, the ligands are here, right? There is no ligand on z axis. Similar to that, this is the x axis we considered, na? On x axis also there is no ligand, right? We are showing the ligands here on the corners. No corner is along the coordination axis. Similar to that, on y axis also there is no ligand. It is at the middle of the face. It not passing through any of the corner sides of the cube. So which means that no ligand along the coordination axis. It is clear. Okay. The first statement what we are giving, that is very much clear that no ligand is passing through any of the coordination axis. So that means the ligand which are not passing through along the coordination axis, it means that along the coordination axis, whatever the orbital lobes it has the metal ion, d orbital lobes it has the metal ion, thus orbitals never be affected by these four ligands. It is, isn't it? Right. So that when we go in an inner dipole, it will get right. Here we are checking that how does the ligands are positions along the coordination axis. With respect to of coordination axis, we are explaining the ligand positions in the tetrahedral, right? So by which first statement what we are giving, that the no ligand is along the coordination axis, it is clear now, right? So the second statement how we give is, no statement, sorry, no ligand is along the coordination axis. Right. No ligand is along the coordination axis. This is clear, right? So now secondly, how we are seeing that the exact position of ligands, right? By looking here on two-dimensional picture, the ligands may be slightly closer towards the y coordination axis, right? These two ligands, but actually that is not correct, right? So when we are taking the model, it will give you perfect position, exact position of the ligand site, right? So ligands, right, they are not along the coordination axis, right? And they are also, the ligands also never be exactly middle of the any of the two coordination axis, right? They are not any of the coordination phase, right? If you are saying that xy phase, right, in between of x and y coordination axis, there will be the plane, xy plane will be there, right? That is what, like this, like this it will passes through along the phase of the xy coordination axis passes through like this, right? It will be along the x axis and y axis, right? On that phase also there is no ligand, right? In between the two coordination axis also there is no ligand. Is there here any ligand? No. It actually, the ligand is occupying the alternate corners of the cube, right? It is not at the edge, center of the edge, right? It is the ligands are occupying the corner position, right? So the phase, xy phase will not have any ligand. Similar to that, the z and y, this is the what phase, right? Z and y phase, right? It will passes through like this, middle from the cube, right? Even this phase also there is no ligand. Here there is no ligand, even here there is no ligand, even here there is no ligand, right? Along the face of the uh, uh, coordination axis also there is no ligand occupying there. What we can say, the position of this position with respect to of coordination axis is, it actually middle of the three coordination axis, right? From here to here, from z, x, y, this position is exactly same distance. It has the whatever the distance it covering here, here and here, with respect of z, with respect of x, with respect of y, it is same. So with respect of all three coordination axis, it is occupying the middle position, right? Middle position, right? So we can also say that in between the any two coordination axis, or we can say that on any coordination plane, such as on xy plane or yz plane or zx plane, no ligand is passing, or no ligand is present. no ligand is present, right? Even in along the in between of any two coordination axis or any of the coordination plane also, there is no ligand is found, right? But the ligands placed are present exactly middle from all three coordination axes, isn't it? They are, from the model you will get the perfect picture, is they are exactly middle from the coordination axis or not, right? If we are taking this particular ligand, right, whatever the distance is covering from the z, same the distance it cover from the x, from the y also, right? Where the coordination axis it passing through exactly middle of the cube face, nothing but from the cube to corner, right? Center of the cube, center of the face of the cube to corner will be the same distance, right? Here whatever the distance, the same distance here also it takes place, and here also there is a same distance, right? Like that the ligands are occupying the position that they are middle from the all the three coordination axes. Here this particular ligand is exactly same distance from all three coordination axes. If you are going with this particular ligand, it also middle from the all three coordination axes, right? And even we are going with the next ligands, the bottom ligands, this particular ligand also middle of the all three coordination axis, and this particular ligand also middle of the all three coordination axis. Like that they are, the ligands are positioned with respect of coordination axis is they are middle from all the coordination axis, right? So when this is how the tetrahedral occupying the position in the uh, cube and with respect of coordination axis, how does they are affecting the valency d orbitals in the metal ion when we take, when we consider that, right? Initially without interaction of ligands, which means in free metal state all the d orbitals will be in a lower energy state, where when the ligands approaches, when the four ligands approaching and forming an tetrahedral complex, where the d orbitals, valency d orbitals of metal initially slightly get excites, ml4 complex d orbitals, and this excited state of d orbital never be stable, they undergo in splitting, they undergo in splitting, right? So here if we are talking each orbital interaction with all four coordination ligands, right? When we express that, there we will give you the splitting pattern that results the splitting pattern of d orbitals, right? So initially we are considering the dxy orbital, right? We know that the dxy orbital has the four lobes in between the coordination axis of x and y, right? In between of xy coordination axis there will be four lobes will be present for the dxy orbital. So when that gets, right, here on model we will explain you how the dxy orbital, the dxy orbital is, this is the x coordination axis, this is the y coordination axis. The lobe, how it takes place is it will be on this particular xy plane at the middle, right? Here will be the one dumbbell lobe will be there, and this is y and this is x. At the middle of these two there is another lobe here, another lobe here, exactly like this, right? Exactly like this, one another lobe will be there. Same x and y, the lobe will be here, the lobe will be here, and here x, here y, and the fourth lobe will be here, right? The first lobe occupies here in between the x and y, and the second lobe will be occupied in between the x and y here, and the third lobe from the x and y here it will occupy, and fourth lobe in between the x and y coordination axis here, like this. Here at the middle here there is one dumbbell, at the here position there is another dumbbell, on here middle position there is one dumbbell, and in between of here the other fourth dumbbell will be occupies, right? So the orbitals lobes will be here at the xy plane, on the xy plane, and they are in the middle of the coordination axis, right? So that is how the dxy orbital lobes. So with respect of those orbital lobes, ligand interaction, the orbital lobes with respect of ligand interaction, if we consider the lobe is here and ligand is here, the lobe to ligand distance will be very much low, right? The distance covering from lobe here will be one lobe, that lobe from the this particular ligand side, the interaction, right, may not be direct interaction. The ligand is directly not towards the any of the xy orbital lobe, but it is slightly nearby the orbital lobe of xy. So here is the lobe, and for that the distance covering from the lobe to ligand is slightly lower, right? With respect of these certain smaller distance, the ligand, right, may not be taking direct interaction with the ligand, but it can be have the partial sidewise interaction. Partial sidewise interaction it arises, right, with the lower distance from the dxy lobe to ligand side, right? This particular lobe will be affected by this particular ligand, and here what we are expecting, the lobe that could be affected by the this particular ligand. Either two, whatever having here the lobe and here the lobe, they will be affected by the donor ligand sites, right? Here this particular lobe will be affected by this particular ligand, and this is the lobe will be affected by this particular ligand. So which nothing but all the four ligand sites will have sidewise partial interactions with the dxy orbital, right? They are affecting sidewisely in partial, they are having negative repulsion interaction with dxy lobes. All the ligands will affect them dxy orbital in an partially with sidewise, right? So with the effect of that, it will be get destabilization, and when it get destabilization, to get stability it arises its energy and reaches to certain higher energy level, right? So like that the dxy, same to that the dyz also, it is also having the lobes in between the coordination axis of z and x, right? So z and sorry yz, dyz we are explaining the orbital how it is interacting with ligand sites, right? Y is here, z is here, right? And y is here, z is here, right? And y is here, z is here, right? Like that the coordination axes are like this. So here the orbital lobe will be how it will be here, in the position of here there is one lobe, here the second lobe, here will be third lobe, and here it will get the fourth lobe, right? In between the y and z and y, there will be one lobe will takes place, right? Here in between the z and y, here another lobe, same to that y and z there is one lobe, like that here one, second, third and fourth, right? So same, right? As such the xy having the lobes, these yz lobes also they are getting closer interaction with the ligand side, sidewise interaction, nearby interaction, sidewise interaction can be possible for even for the YZ orbitals also, right? The distance covering from the dyz orbital lobe to ligand site is very much nearby. They may not be directly having any interaction, but there the sidewise interactions are will be possible, right? The possibility of sidewise interaction of dyz of this particular lobe and this particular lobe will have interaction with here ligand, and here lobe will be affected by this particular ligand site. Same to that, this particular lobe will be have interaction with this particular ligand, right? Which nothing but all the four lobes of dyz also get in participation of sidewise partial interaction with all the four ligands, right? The dyz orbital lobes 4 also get interacted with them all four ligands of tetrahedral complex in sidewise partial interaction as such of d xy orbital. So same effect it is going on as such of xy. So for that yz also get enhances its energy till to d xy orbital. Same when we are expecting the excitation by zx orbital also, d zx orbital also will have partial interaction with the all four ligands, where the d zx orbitals also will be slightly closer towards the all four ligands, so get interacted and gets excited into higher energy levels such as dxy and yz, right? They reaches to certain this particular energy state, right? And thereafter the left fourth orbital, if we consider dx square minus y square, this particular dx square minus y square has the lobes along the coordination axis, right? It is axial orbital, it has the lobes along the coordination axis. Along the x axis there will be two lobes, along the y axis there will be two lobes, right? So here if we consider the interactions of ligand with towards the dxy orbital is, the lobes are, this is x orbital, this is y orbital. The lobes along the x orbital, x coordination axis, there is two lobes. Along the y coordination axis there is another two lobes, right? So these particular orbital lobes, right, dx square minus y square orbital lobes are having slightly higher distance, right? Having slightly higher distance from the ligand side to lobe. So far here there is no interaction is possible, right? When we are going with an xy orbital lobe, it has slight lower distance, right? Having lower distance, the sideways interactions are possible. But here from the x orbital lobe to ligand side, the distance covering is very much larger. This slightly higher distance from the xy orbital lobe to ligand, the x square minus y square orbital lobe to ligand distance is slightly more, right? This slight more distance from the lobe to ligand side uh, will negligible will overcomes the interaction of ligand side to that particular dx square minus y square interaction, right? The repulsive interactions are here slightly overcome, right? So when it is the interactions are overcome, which nothing but there is no interaction between ligand side to dx square minus y square orbital. So this particular dx square minus y square orbital get stabilizes and reaches to lower energy, decreases its energy to lower energy side, right? Same all the four orbital lobes of dx square minus square dx square minus y square has distance is more from the ligand side to orbital lobe. So whatever the distance covering here, as it is having in more distance, there is no interactions are possible here, right? The no interactions are expected here. As there is no interaction, negative interaction, it gets stabilizes, reaches to lower energy. Same to that, the next coordination orbital, next orbital d z square orbital, next axial orbital dz square orbital, that also having lobe along the z axis, two dumbbell lobes on top and down, the spherical smaller spherical at the middle, right? The spherical, as if it's having smaller size, the distance covering from that to ligand sides is very much large, and the lobes which are along the z axis also having larger distance from the ligand sides, right? All the ligand sides, no ligand will interact with the d z square orbital, having larger distance from the orbital lobe to ligand side. There is no interaction. When there is no interaction, that particular orbit also get decreases its energy and reaches to lower energy level, right? So when all the five orbitals, when they are interacting with ligand sites, such higher energy state of triply degenerated state will generate, which is termed as T2, and the lower energy state is doubly degenerated state. Doubly degenerated state, it denoted with E. Right? So like this it happens, and when we go with the excitation energies of T2 and lowering energies of E, that can be given as the excitation is plus 0.4 delta T. Value energy is excited by T2 orbitals, and minus 0.6 delta T energy, the E orbitals get decreases their energy, right? This is how the splitting pattern of the tetrahedral complex it takes place. So here the energy distance from lower energy state E to higher energy state E to higher energy state T2 will be known as what? It could be known as crystal field stabilization energy of tetrahedral. It is similar as octahedral crystal field stabilization energy. Energy distance between the lower energy to higher energy will be known as crystal field stabilization energy. Crystal field stabilization energy, CFSE, of tetrahedral complex. Tetrahedral complex, right? And it could be calculated as CFSE is equal to 0.4 delta T into electrons of T2 minus 0.6 delta T into electrons of E. Right. So the note point also here we can have, when we compare the splitting pattern of tetrahedral complex with octahedral complex, we know that the octahedral complex having lower energy is T2G, higher energy is EG. This is what the d-orbital splitting pattern in octahedral transitional metal complexes, where the non-axial orbitals are having lower energy and it is stated as T2G, and the axial orbitals are enhances its energy, reaches to EG energy state, right? So which is quite reverse with respect to of tetrahedral splitting pattern. In tetrahedral splitting pattern, the axial orbitals are getting in lower energy as E energy state. The non-axial orbitals are getting enhances their energy and stated as T2 energy state, right? Which is quite reverse to one to other. So in comparison, the tetrahedral d-Orbital splitting pattern is exactly reverse to the d-Orbital splitting pattern in octahedral complexes. Is it clear? Is it that? This is what octahedral, where Eg is higher energy, T2G is lower energy. Here, when it comes in tetrahedral, T2 is higher energy, E is in lower energy.